Hello everyone. In this first video, we will look at of how we could come up with a recursive solution for the operation of searching in a binary search tree. The definition of binary search tree itself is recursive, right? So we understand for every node which exists in a binary search tree, all values in its left subtree are lesser and all values in the right subtree are greater. But we also understand that all values on the left subtree are also a binary search tree, right? So for every node, there's a binary search tree to the left and there's a binary search tree to the right as well, right? And that's if it exists, and if it doesn't exist, it's null, right? So, so there are most operations on a binary search tree which could be recursive. Yeah, we will see the first one today, where we will figure out of how I could write a recursive solution for search operation. We have learned of how we could do it iteratively in our class, right? So let's get started. So what you see here is a BST with 5 nodes, and I'm being given the address of the root node, this root node 25. So for any recursive solution to be written, there are two conditions. One is that there should be a base condition or a terminating condition. And the second one is that the problem size should keep reducing, right? So what might be the terminating condition when I'm doing search, right? So let's figure that out. Before which, let's write the prototype. So I understand when I'm writing the routine search, I should be told from where to start. So let's put struct node star root, which is one of the arguments to be given to us. And the second argument would be to tell us what is the key value that is to be searched, right? And let's also go ahead with the fact that there's no return type, yeah, where the search routine will only print if a search was successful or not successful, right? So this would be the signature of the routine, recursive routine search, yeah. Uh, let's figure out the base condition. So I understand the search that I'm trying to do might be successful or might not be successful, right? So let's put those two conditions as the base condition, right? So base condition one, that the key is not found, right? So if you are in the process of searching and at some point of time you end up root becoming null, yeah, that would mean that the search was unsuccessful, right? So let's write that printf statement. So I say if the root is null, I say printf, it's an unsuccessful search. You ended up moving from the root, you dropped down to a null value and you couldn't find the key, right? So you say unsuccessful. And I understand after I know that it's unsuccessful, I have nothing else to do. So I will stop my recursive call. I say return, right? But let's say it's a successful search. So that's the second base case where if I find that I've found the key, and that is the second base condition or the terminating condition where you start moving from the root. Let's say you're searching for a value 22, right? So what would you do? You will jump from 25, you will move to the left, you will move to the right, and you are actually standing at the node 22, right? So that would be your root, and that is the same as the key that you were searching for. So let's put that as the if condition. So if you're standing at a value at the root a node whose data field is the same as the key that you were searching for. Yeah, so if this condition is true, I understand I should tell my user that the search was successful. And nothing else to do, let me return. Yeah, so the two base conditions are clear here, where I found the key or I don't find the key, right? But what is the recursive part, as in how do I reduce the problem size? It's pretty simple for the reason that, when I'm searching for a value, let's say 1 second. Let's say I'm searching for a value. I understand, I compare it with the root, then I make a decision to jump either to the left subtree or the right subtree. And what we say is, again, the search is on a smaller problem size or a smaller subtree. Correct. So let's put that recursive call here. So I say, if at all, if at all the key that I'm searching is lesser. Yeah, the case that we see here, let's say I'm searching for 22, which is lesser than the actual value in the root arrow data. I understand that the searching need not happen anywhere else, but has to happen in this left subtree, correct? So the bigger problem where I had to search among 5 nodes is now a task of searching among these 3 nodes. The problem size is reduced, correct? So if you find your key lesser than the roots data, I understand that, my search, let's call the recursive search. So I say search in the chota subtree. And how do I know what is that subtree? I have to say this should be a new root. And who will give me the address of this 20? 25 ka left, correct? So I will say root arrow left. Please jump to the left, and I say search for the same key value, right? The search key doesn't change. So it's the same key value which continues to be searched, but now in a left subtree, right? But what if it's the other case? Yeah, the case that, let's say you were searching for, not for value 22, but let's say for a value 40. Yeah, I understand from the root of 25, I will have to jump, search in this subtree, correct? And that would be the else clause. I say else search in the right subtree. And how do I go to the right subtree? That's the recursive call with the argument, first argument being the address of the right subtree, and the key value would remain the same, right? So that completes the task, because as you could see, I either search, keep moving, I search in the left or the right, and the terminating conditions, which are basically the base conditions, are when the root becomes null or you find the key, right? So we've handled all the cases, and this forms the complete recursive search operation on a given binary search tree. Thank you.